All right, today we're going to crack a classic C programming puzzle. It's one of those things that trips up pretty much everyone, whether you're a student getting ready for an exam or even a coder who's been at it for a while. We're going to take a deep dive into how functions handle your data, and by the end of this, you'll spot the most common mistakes from a mile away. Okay, let's just dive right in with a mystery. Take a look at this code. On paper, it looks perfectly logical, right? It's supposed to take two numbers, A and B, and just swap them. But when you actually run it, nothing happens. The original values don't change at all. It just fails. So what gives? Stick with me because you're about to find out exactly why this happens. So to solve our little puzzle, we've got to quickly review our tools. Go back to basics for a second. Every single function in C has three fundamental parts, and really getting these down is the first step to figuring out why our code is acting so weird. Let's start with a quick pop quiz. You've definitely seen a line like this before, usually hanging out at the top of a C file, way before you even get to the main function. What's its official name? What is this thing actually called? Yep, it's a function prototype. And honestly, the best way to think about it is like a movie trailer. It just gives the compiler a little heads up, a sneak peek, saying, hey, a function with this name, this return type, and these kinds of parameters is coming later, so don't freak out when you see it being used. Next up, we've got the function definition. Now, if the prototype was the trailer, this is the main feature film. It's the actual block of code, the nuts and bolts, the instructions that do all the heavy lifting when the function gets called. And of course, the function call. This is the moment of truth. This is when we actually tell the function, okay, go time, and give it some real values to work with. So, we've got the trailer, we've got the movie, and we've hit the play button. Why does our swap function still fail? Well, the answer lies in a really fundamental rule about how C passes data around. This is our first major clue, and it reveals the default behavior for pretty much every function in C. Let's call it the photocopy rule. So here's the absolute crucial point. When you call a function in C, it doesn't trust that function with your original variable. No way. Instead, it makes a quick photocopy of the value and sends that photocopy over. Your original data is kept safe and sound completely separate. Let's just walk through what's happening here, because this visualization is perfect. So in main, we have our variable a just sitting there holding the number 10. The moment we call the function, a brand new temporary variable, let's call it x, is created inside that function's little world. Then the value 10 is copied from a to x. Now whatever the function does, it's only doing it to the copy, to x. When the function finishes, x just vanishes and our original a is left behind, completely untouched. And boom, there it is. That's the solution to our mystery. Our broken swap function was actually working perfectly fine, but it was only working on the temporary photocopies. It swapped them like a champ, and then as soon as the function ended, it threw those swapped copies in the trash, leaving our originals exactly as they were. So if we can't change the originals with a photocopy, how in the world do we give a function permission to modify our actual data? It's simple, really. We stop sending a photo of the house, and instead we send the house's address and a key. This powerful technique is called pass-by-dress. It's how you let a function reach outside of its own little bubble and directly change data somewhere else in your program. And the way we do it is with pointers. Now, to make this magic work, we need two special operators that are like a dynamic duo. First, you have the ampersand. Think of that as the get address button. You put it in front of a variable and it tells you its exact location in memory. Then you have the asterisk, the star. That's your key. It capes that address and says, okay, I'm going to unlock this location and access whatever is stored inside. All right, now that we have our keys, our pointers, let's go back and finally fix our broken swap function once and for all. And here is the grand reveal. On the left, our original failing code. On the right, the solution that actually works. Notice the two critical changes. When we call the function, we're now passing the addresses of our variables using that ampersand, and the function definition itself has been upgraded with asterisks to say, hey, I'm not expecting values anymore, I'm expecting addresses, I'm expecting keys. It now has permission to change the originals. So we have two completely different ways to send data to a function. Let's put them head-to-head for a final comparison. Understanding the trade-offs here is exactly the kind of thing that separates a novice from an experienced C programmer. This table is basically your ultimate cheat sheet. Pass by value, the default, sends a copy. It's super safe because your original data is protected.
Pass by address sends the memory location, the key. It's way more powerful because you can actually change the original data. But with great power comes great responsibility. Your original data is now exposed.
Okay, let's boil this all down. If you were cramming for an exam, what are the absolute must-know, can't-forget takeaways from all of this? Here are the 4 things to burn into your brain. 1. The prototype is just a promise to the compiler. 2. Pass-by value is the default. It sends a safe little photocopy. 3. Pass-by address is the powerful one. It sends the key, the address, and lets you change the original data. And 4. That swap problem? It's the classic test of this entire concept. If you get that, you get this. And I'll leave you with one final thought to chew on. You now have the power of pointers, the ability to modify data anywhere in your program. But when might you intentionally choose not to use that power? When is the safety of the good old photocopy actually the smarter, better, and safer choice for your code? Answering that question, well, that's when you really start programming.